All right. Hello. Can everyone hear me? Awesome. Hi, I'm Thomas, product manager on WebAssembly.
And I'm Brad Nelson, tech lead manager on WebAssembly.
And today we want to talk to you just for a little while about WebAssembly and some of the progress that we've made throughout this last year. So first of all, WebAssembly, low-level bytecode for the web. I think hopefully everyone in the room knows the basics, but it's a way for you to compile C++, run it performantly in the browser, et cetera, et cetera. In the last year, we had all 4 browsers now shipping WebAssembly, which is really great news, and actually makes WebAssembly the first essentially new bytecode format for the web since JavaScript was invented more than 20 years ago. And this year, as a general focus of 2018, we want to emphasize on improving the developer experience of creating WebAssembly, interoperating better with JavaScript and the rest of the web ecosystem, as well as continuing to advance the standards with basic features and improvements. So what does WebAssembly actually mean for developers? Well, WebAssembly really comes down to performance. And you can actually unlock a lot of different things within the web platform through that performance. And so first of all, this opens the doors of including more performant logic in applications and doing just things that you couldn't previously imagine doing on the web, like video editing and Photoshop, now being brought to the web. You can also utilize WebAssembly's portability and its ability to compile from C++ and other languages to now make that rich ecosystem of content available to the web and the web platform. And lastly, you have the option of doing more things with languages and frameworks, and we'll get into the more technical details of all of these things later on. But I also want to highlight some of the awesome use cases that we've seen for WebAssembly over this last year and some of the many partners that we've worked with in using WebAssembly to bring great experiences to the web. And so one of the big ones that we like to highlight is AutoCAD. And they succeeded in taking a 35-year-old code base, a code base that literally predates the web itself. And they were able to port it to WebAssembly and now host and release an application on the web for AutoCAD. To me, AutoCAD also represents kind of the spearhead or vanguard of what I think will be a whole new class of applications that come to the web, applications that are performance intensive and that you previously couldn't do on the web, but now they get to take advantage of the linkability of the web, the universality of the web being available on every platform or on every device, and the ephemeralness of the web, meaning that your application is there when you need it and gone when you don't, and there's no install friction. Another application along the same vein that was able to make the transition from native to the web is Google Earth. And they will be especially excited about thread support, which we will also be adding to WebAssembly in the next coming months. Another kind of general usage pattern that we see for WebAssembly is games. And I'm happy to say that both Epic and Unreal game engines have now shipped. Unity and the Unreal game engine have now both shipped support for WebAssembly, meaning that the entire collective wealth of the games created in both of those engines can now be exported to the web. Another interesting application that we saw is a range of visualizations of legacy financial applications. This one's interesting to highlight because it was one of those surprises to us where we just really didn't think of this as an application. But turns out that there are many kind of nuanced and niche ways that people are looking for performant logic. There's also a rich plethora of libraries that can utilize WebAssembly. One of the interesting ones that we saw was facial recognition, where you now have these libraries that you want to be really performant so that you can have a good experience, like facial recognition that needs to do heavy computation. And this is really done very successfully through WebAssembly. Another one is a barcode reader, where we found a partner that wanted a barcode reader. They had been trying to go through the standards process and had been making headway. But as we all know, working on the web platform, it can take time to develop these standards and actually get them shipped to all the browsers. And so they realized that they could actually take a C++ library for reading barcode scanners and just port it to the web. This means that you not only have to not wait for the web standard to actually advance, but you also can better polyfill your functionality in older browsers. Another area that's really rich use case for WebAssembly is codecs. And so this includes video decoders that can serve as polyfills, once again, similar to the barcode scanners. And it's the same story for images, for instance, polyfilling WebP, and soon maybe more niche formats like FLIF. And then lastly, there is the idea of doing 3D codecs for models for instance, Drago codec is deploying using WebAssembly. Another area that's really interesting to explore as a use case for WebAssembly is the idea of bringing more languages to the web. So through WebAssembly, we today fully support C, C++, and Rust, which is a huge ergonomic benefits to developers who prefer maybe to not write specifically JavaScript, which was previously the only option. There's also a number of other languages and frameworks that are currently working on adding support, including .NET and Kotlin, which have both shipped experimental support and are kind of testing it out in the field. There's also a total of 25 separate languages that are being tracked on GitHub that are trying or working towards adding support with WebAssembly. One interesting one that I thought would be cute to end on is to highlight cases where WebAssembly is actually useful outside of the web platform. WebAssembly was specifically designed with the intention that it could have other applications. And one of the ones where it's actually been really picked up is in blockchains. And so for those of you who don't know, blockchains also extend past Bitcoin. There's the idea of doing kind of these logic executing contracts through blockchains. And this is an area that's been really taking off in the startup community. And it turns out that WebAssembly is a perfect use case for this because of its security properties of being able to run untrusted code without having any knockoff effects. And so this is really useful for that ecosystem. So useful, in fact, that we have lost not one, but 2 team members from the WebAssembly team to blockchain startups. But the good news is that they are all still working on WebAssembly just now from those different companies, which is really just bringing more resources to the WebAssembly effort.
All right, so now we're going to talk a little bit about things that are on the horizon. The WebAssembly standards process is incredibly vibrant. We've got, the last time I checked, 18 different active proposals in flight. I'm going to start with the one that's sort of, I think, the most impactful, but it also has some challenges, threads. Obviously, the web platform desperately needs shared memory. Unfortunately, we recently lost our access to shared memory due to the Spectre exploit. Fortunately, the Chrome team was already working on a technique called site isolation, which offers us a path to being able to return shared memory to the web in a secure form. We're expecting that the shared array buffer will be re-enabled sometime shortly after M67. And following shortly after that, we hope to bring threads to WebAssembly. The way that we've incorporated shared memory threads into WebAssembly is by reusing surfaces in the web platform. So we reuse workers as threads. They run WebAssembly modules that all talk to WebAssembly memory, which is backed underneath by a shared array buffer. That shared array buffer is then provided to the various APIs in the web platform, such as WebGL and WebAudio, allowing you to talk to all the other surfaces that you'd like to in the browser. Really excited about this. This, is the sort of the opportunity to have NX performance wins for applications, and it's crucial for a number of legacy applications that have the expectation that your application can block. SIMD is simmering along. We've got implementations in 3 browsers, and the standards process continues to swirl around consensus on this feature. This will allow us to unlock the performance of vector processing that is available in contemporary CPUs. We're starting with 128-bit SIMD, and signs are looking pretty good. We're working mainly on toolchain support at this point. Another exciting development is, of course, we're trying to make WebAssembly faster within the things that have already been standardized. We recently shipped streaming compilation for Chrome, and we're working very hard on bringing tiered compilation so that we'll be able to start WebAssembly running fast and then tier up to our highest tier and run even faster as the application runs. One interesting property that WebAssembly has that's somewhat different from JavaScript is that, generally speaking, it tiers only in the upward direction. And so because you have full type information, you typically don't need to de-optimize. And of course, we're also, in general, working to make our WebAssembly implementation the best it can be in all sorts of ways. There's a bunch of smaller proposals that are coming. We've got things like tail call cooking. Multi-return is actually nearing the point that we could think about shipping it, and we have opcodes for sign extension on the way. We're also working on a number of things that for particular communities are especially important. We are starting to clarify how content security policy interacts with WebAssembly. We've sorted that out for those of you that were trying to use WebAssembly in the context of Chrome apps. There's now an option, but we're trying to come up with a pattern for how to do this in general. We have some proposals, a proposal in flight for exception handling. This is especially important if you're actually using C++ exceptions. There's a big performance win. The current solution has a 5 to 10x overhead. And then we're working on operations like bulk memory, so things like a memory copy can be done more efficiently. Another area that we've put a lot of thought into, and there's a number of efforts, they're all interconnected. I'll try to sort of give a broad summary of them here, is that we're trying to improve the ergonomics of WebAssembly and how it interacts with the rest of the web platform. Right now, this is how WebAssembly interacts with the world. You've got a WebAssembly module surrounded by a sea of JavaScript, and it's reliant on JavaScript to interact with the DOM and to interact with web APIs. That's inefficient, but it's also sort of less than ergonomic in terms of how programs are structured. WebAssembly thinks of things in very simple types. There's basically just 4 types right now, long and short integers and floating point numbers. And the trouble is that even not all of these types can be fully represented in JavaScript. Int64s don't have a representation, but fortunately, the big int proposal has now reached stage 3 at TC39. And so this will give us a way in JavaScript to represent an int64. There's a corresponding array type so that an array buffer containing int64s can be pulled out. And this actually mirrors the way in which WebAssembly thinks about loading and storing to its linear memory. Once that's available for WebAssembly, we'll obviously allow those kinds of types to flow in and out. But what we're really excited about is the prospect of making WebAssembly sort of more first class. And there's 2 interrelated proposals in this space. One of them called reference types that will allow you to hold on to JavaScript and DOM objects from within a WebAssembly module. So that you'll be able to pass them into the module, potentially store them in a table, and then hand them back out to the surfaces on the other end. This will potentially reduce the amount of certainly boilerplate JavaScript that we'll have to ship with a WebAssembly module, but it will also mean that the interaction that you have with web APIs will be more natural. You'll be able to wrap up a WebAssembly module to look closer to something like what you would expect from a JavaScript module. There's a related thing called host bindings, which allows you to actually describe the ability to invoke an object method. And the 2 used in tandem will hopefully allow us to not only make this more ergonomic, but also more performant by allowing us to inline the calls out to the DOM and to web APIs and make those calls as efficient as we possibly can. I'm excited that weak refs have finally gotten some traction at TC39. This will solve a number of problems for folks that are interested in weak refs in JavaScript, but one I'm especially excited about for WebAssembly is that it'll allow us to get a finalization signal. And so if you've got a C++ object sitting inside of a WebAssembly module and some veneer that you've exposed to JavaScript, you want to have a notification when that's been garbage collected so that you know when to call the destructors in C++, and that's on its way. We're also now actively working on bringing WebAssembly support to ES6 modules. This will allow a pattern in which someday soon we hope to be able to allow you to reference a WebAssembly module from a script tag. More importantly, you'll also be able to reference it from an import. And so this will allow the possibility for a JavaScript module to do an import to a WebAssembly module to in turn import from a JavaScript module, and to seamlessly interoperate in the way that ES modules were intended to work in the platform. Of course, I don't want to give you the impression that it's terrible interacting with JavaScript right now. There are actually a plethora of options in our toolchain to make the task of interacting with the web platform easier. In fact, if anything, there's too many options. We've got a number of different choices with different trade-offs in our toolchain. And one of the areas in general that we're trying to improve is our toolchain. So for example, you can call out to JavaScript from C++ as straightforwardly as this currently. It obviously generates a number of things behind the scenes, and with all of those proposals I just talked about, we'll be able to make that much more efficient. But in general, the tool space is something that we're working to improve. And it's not just us. The Webpack project is working on providing support for WebAssembly. And the Rust community has been very active in taking the host bindings and any ref proposal and running with that, polyfilling it, and offering bindings in Rust that actually are designed with an expectation that those proposals will come online. And for now, they polyfill them with JavaScript. So you can look forward to a world in which various packages that you bring down will just have WebAssembly, and you won't have to care about it, potentially. We're also obviously spending a lot of energy on WebAssembly's primary toolchain Emscripten. It offers a range of options for C++ programmers. A bunch of things are coming in the very near future, likely in Q2. We're in the process of making the big switch where the default in Emscripten will be to emit WebAssembly code instead of ASM.js. This is a sort of an exciting milestone. In addition, we've been working on a number of improvements in LLVM that are about to roll over into Emscripten. One of which is that we've been working on an upstream backend in LLVM. For a long time, Emscripten used a fork, essentially, of LLVM called FastComp, and work had to continue on that branch, lots of merges back and forth. We're finally going to be able to cut over to our shiny new backend and offer that support directly in mainline Clang and LLVM. And I hope that someday that will actually lead to the possibility of stock Clang in your desk just being able to use WebAssembly. Part of that is that we're also checking off the various items that are necessary to get our backend out of the experimental classification. And so this will allow us to rely on other LLVM developers to make sure that it stays green. They generally actually do keep it green as it is, but this will be a formal milestone. So that's it. We're way fast over time here. We have lots of time for questions. I want to implore you to give WebAssembly a try. I want to implore you to not assume that if you have some application that you think doesn't work on the web, that's not true. WebAssembly can help you do it. And we're ready for questions.
Yeah.
So I'm excited to see that the better support for calling DOM APIs and other web APIs will be coming to WebAssembly. Is there anything special that web API maintainers will need to do in order to support that, or will it just sort of work out of the box?
So in terms of, so there's several levels of performance that we're hoping to get out. In terms of the ergonomics, that should be something that API developers won't need to worry about. But if you want to get performance, there may be some steps in Blink that will be required. We're actually still sorting out exactly how we will optimize those boundaries, so there'll be some effort there. One additional thing to think about as API developers is that although in the host bindings proposal we've talked about the idea of optimizing the conversion of various types, things like property bags and enums, there's an ongoing conversation about how far we go in that direction, how automatic we make that kind of thing. And so something to think about as web APIs outside of WebAssembly develop is that you want to make sure that those APIs can get the best performance they can. So for example, if they're dealing with lots of memory buffers, think about whether that can be one big buffer, because that works better with WebAssembly. Think about if that can be shared memory, because again, that means that you can potentially offload that work to other threads and use this primitive that we now have in the platform to talk about shared memory. Think about whether it needs to be async or whether it's something that can happen with other kinds of synchronization, if that's the optimal pattern. Depends on the API, depends on the purpose. And also, of course, think about whether you can express the API in simple types. Yeah.
Is sync or async preferred? Like, which will be easier?
I think it depends heavily on the API. I think the general pattern of the web has obviously been to do asynchronous programming, especially if you're on the main thread, especially if it's something where you've got other things going on. If it's something where there can be sharing on a worker, you have the option, and it depends.
Okay, I just want to be sure that it wouldn't be easier to call, say, a sync API or an async API. No, particularly difficult to call as async.
No, it should be comparable.
Okay, so. Thank you.
There is a slide to show the WebAssembly can call the web API directly. Mm-hmm. means it doesn't need to go through the JavaScript to call the web API.
Yeah. So the way this will actually work is that you'll import a JavaScript function. That function will be something that the engine can recognize as a particular function, and it can actually optimize and skip over the JavaScript frames in between. So it's not that we're providing some sort of bindings path to the rest of the platform. It's rather that we're allowing, when we recognize that oh, I'm calling into JavaScript, which is, or sorry, I'm calling into a function that came from a web API, that we can skip over those.
So this is done by the browser, not the WebAssembly itself.
Yes, will be implemented in the engines. So,
Thank you.
yeah.
Hi, thanks a lot for the talk. Since I saw you were talking about SIMD, I just looked at the TC39 spec, and it doesn't include anything with float64. Any reason for that?
So the TC39 SIMD proposal, that's got the SIMD.js proposal. That one's gone. With the WebAssembly proposal, we have talked about gone back and forth on float64 by 2. The main issue with that one is that it actually carries back to that history with TC39 and SIMD.js. In the JS space, we were very concerned about whether we could offer the identical behavior, whether it was desirable rather to offer identical behavior in terms of things like denormals with float64s. I actually think that it's likely that for WebAssembly we can choose to make a different decision in that space, but it's still actively open. If you have a use case that would benefit from float64, I would encourage you to reach out to the WebAssembly community group. That's still sort of up in the air. There's certainly something where we could do it.
Okay, thanks a lot. I guess float64 is not very useful for many people, but in scientific computing, it's essential.
Mm-hmm.
All right. Thank you so much, everyone. And please come find either myself or Brad as you see us wandering the halls throughout the rest of the day and tomorrow. And of course, feel free to reach out.